This is part 2 of section 4.5. We're talking about the properties of tangent, and now we're going to talk about the even-odd property. We already know that tangent is an odd function. And so when we're talking about a graph of a function that is odd, that means it's going to be symmetric about the origin. That's going to help us get our graphs from here. So in summary, the domain of tangent is all real numbers except odd multiples of pi over 2. Okay. The range is all real numbers. Zeros or x-intercepts are all integer multiples of pi, or we could write it as x equals n times pi, where n is some integer. Our period is pi. We have vertical asymptotes at x equal to odd integer multiples of pi over 2, which is this, and that's actually saying the same thing as right here. Where everywhere this doesn't exist, we're going to have a vertical asymptote. And it's an odd function, so we have origin symmetry. So let's actually get the graph of tangent. Here you have some values of tangent. They've just computed these and have approximations in here. We're going to use it to build our graph. Okay? We know that pi over 2 is a vertical asymptote, and you can see we're getting closer and closer to 1 over here, and our numbers start jumping up quite dramatically. When we get close to a vertical asymptote, period, in any kind of graph, our graph is either going to go to positive infinity or negative infinity right at that vertical asymptote. Okay, and right here, we're going up. Okay, if we plot these points here, okay, we have from 0 to pi over 2, and we start plotting our points, you can see that it ends up going up pretty dramatically. Now, this is only half of a period. Our period is supposed to be pi, and we only have pi over 2 drawn. Well, we know we have origin symmetry, so if we figured out this much, then we can figure out the rest of it because of symmetry. So this is the graph of one period of tangent. Okay. Now we know that tangent is periodic, so the graph is going to repeat itself. And if we just repeat that over multiple intervals, you'll see that you have this. It's just going to be repeating that basic graph over and over and over again. Okay. Now, of course, we're going to talk about graphing things that are more complicated. Now, everything I'm talking about here, you can do using shifts. So we know how to do vertical shifts and horizontal shifts and stretching and compressing. All of that still works, but we do have different vocabulary here. So the chapter heading, or the section heading in the book, is graphing y equal to a times tangent bx minus k. Really, you want to start off writing your function like that. So that would mean factoring that b out so that you can have something in this form. Now, often the computer is going to ask you to write your answer in this form, multiplied out, but this is where we'll start. Okay? With sine and cosine, we found the amplitude, the period, and the phase shift. Well, this doesn't have an amplitude, meaning that it goes the same distance above and below over and over and over again. But we do have vertical stretch factors, and it just happens to be called amplitude with sine and cosine. We find this the same way we have with everything else. What would have been the amplitude in sine or cosine, meaning the number in front of our trig function, is our vertical stretch factor. Works the same way. Okay? The period is pi over b. Now with sine and cosine have a period that's 2 pi, not pi. And when we wanted to find the period of something that was in this form, we did 2 pi over b. Well, here, the period of tangent is just pi, not 2 pi. And we divide by b. So that's the same sort of pattern. You take the period of your function and then divide it by that number that's right there. And then your phase shift or your horizontal shift is c. So this is very similar. This is just a different name right here, but it's the same basic concepts that we have been dealing with. Okay? So after we found these, we need to talk about where our vertical asymptotes are. Okay? And we know that we have vertical asymptotes at odd multiples of pi over 2 whenever your argument is an odd multiple of pi over 2. Here's our whole argument right here, the bx minus c, b times x minus c. So we set those equal to adjacent asymptotes for just plain old tangent x. And then we solve each of those, and we'll find 2 asymptotes. And then we're going to break that interval up into 4 equal parts. So you take the period, which is right here, and you're going to divide it by 4. We're going to break it up into 4 pieces. Then we're going to find 3 function values, and then get the graph done. Okay, so let's try this. We want to graph y is equal to 3 times tangent of 2x minus pi over 2. Well, the first thing I need to get this value right here on the outside. So I'm turning something that's in this form into this form. So this would be equal to 3 times tangent of, factor out a 2, and that becomes x minus, that's pi over 4 now. So if we want to identify our a, b, and c, our a value is 3, our b value is 2, and our c value is pi over 4. Okay, so our vertical stretch factor is 3. Now for the period, that is pi over b. So our period here is pi over 2. And our phase shift is c. So that is pi over 4. Okay, so what we've done is we've made it through step 2 here. Now we're going to find 2 adjacent vertical asymptotes. So I'm going to take the argument and set it equal to negative pi over 2 and then pi over 2. So I'm going to use the multiplied out form just because it's going to make it a little bit easier. So I'm going to set it equal to first negative pi over 2, and then I'll do the same thing again, equal to positive pi over 2. Okay, so here if I add pi over 2 to both sides, I've got 2x is equal to 0, so x is equal to 0. I have a vertical asymptote at 0. Here, if I add pi over 2 to both sides, I get pi. So x must equal pi over 2. So these are my vertical asymptotes. Okay, so let me go ahead and put those on my graph. I have one at 0. I'm going to go off to the side just a little bit so maybe it can show up. And I have a vertical asymptote at pi over 2. Okay. All right, so what else do we need to do? We need to divide the interval into 4 equal parts of length 1/4 pi over b. Well, pi over b was 1/2. If I multiply that by 1/4, I get pi over 8. So basically, I'm going to break this up into pieces that are pi over 8 apart. So I have here 0, 0, and if I go over pi over 8, I'm going to find f of pi over 8. I'm going to find f of pi over 4, because that's 1/8 further on. And then what's next? If I add pi over 8 again, I get 3 pi over 8. Okay. Now, if you go to your calculator and you plug this in, you get -3. Here, you get 0. And here, you get +3. And this is how it should be, because this is our vertical stretch factor. Okay? And basically speaking, if you break it up into equal parts, if you're just graphing tangent, you're going to have -1, 0, and 1. So each of these has been multiplied by a factor of 3. So basically, I have at pi over 8, I'm down here at -3, and then at 0 here, and then at +3 here. Connect it as smoothly as possible, and it is a curve, even though it looks a bit like a line. I'm sorry, this is not good. That should be more curved like that. Okay, and then if you're asked to repeat it, you would draw in another vertical asymptote, the appropriate distance away. And then you would just basically repeat. And hopefully do a better graph this time. And you could graph as many periods here as you need to.